Okay, so the last one, we are going to do the analysis, the failure analysis due to normal stress, bending moment, basically. Okay, so this is mode 3. So we know that we are to construct our bending moment diagram. Okay, we are just going to focus on the positive. This is our moment. This is 0. This is 48. And this is going to be our 96x. And this is our inches. And we know that the maximum bending moment will occur at the center. This is because the shear force is equal to 0. Okay, but what is this value? Right, so we know that this is how our shear force diagram, bending moment diagram will look like. Okay, so we know that this value over here, so the force is P/2, the perpendicular distance is 48, so this is equal to 24 P pound inch. Okay, so mode 3 is failure. I do apologize, I'm rushing too quick. Mode 3 is due to failure due to normal stresses acting in the wood structure. Okay, so we know that the maximum bending moment is 24 P pound inch. So the formula that we're going to apply is stress in the x direction. The maximum is equal to mz over izz multiplied by y. Okay, and the maximum normal stress allowable is 8,000. Okay, so 8,000 times 10 to the power, no, not 8,000, 8 times 10 to the power 3. Then this will be equal to 24P. Y is equal to 5 plus 4. And IZZ is 2902. Okay, so therefore P is equal to 8 times 10 to the power 3 multiplied by 2902 divided by 24, and then we have a 9 down here. So the P will be 8 power 3 times 2902 divided by 24 divided by 9 is equal to 107.481 times 10 to the power 3 8-pound force. Okay, pound force. So what we see is, if we consider failure due to bending moment, the force is the highest. Okay, the second highest will be due to the shear force, and the third, or the smallest value, will be due to the failure at the joint. So therefore, you take the smallest value. P allowable will be equal to 6910 pound force, which is controlled by the joints. Okay, so always, okay, that if I mean, calculation like this is pretty interesting, right? So what is it trying to tell us is the weakest link of a structure is always the joint, and that's always true. Okay, if you're going to beat someone up, or if you are under attack, right, and the person is twice your size, where do you go for? Go for the joints, right? It's natural. Now we know it. Okay, I'm going to do a few more examples. Why is always very difficult. Okay, it's not impossible. It's difficult to. So the level of difficulty is this. Okay, the problem is the difficulty in this section is what first moment of area to consider. It's always the most confusing question. Okay, I'm going to highlight this. Okay, it's going to be always, student get it wrong is always, what is the first moment of area? Which is the first moment of area to consider? Okay, so let's look at another problem. So let's look at a different problem. Okay, so this is our example number 2. Okay. Okay. Okay, so this is our cross section. Okay, so the box beam is constructed from 4 boards that are fastened together using nails along the beam. There are spaced every 2 inches. If each nail can resist 50-pound force, determine the greatest shear V that can be applied to the beam without causing failure. Okay, so this is a very interesting structure, right? So you have a flange. Okay, so you have a top flange, which is held by 2 vertical nails, and then you have the bottom flange, which is held by 2 horizontal nails. Okay. Okay. So the thing is, the formula we know from here, right? The formula that we're going to use is Q is equal to VQ over I, and is equal to force or resistance force of the nail divided by spacing. Yeah, divided by spacing. And the resistance force of the nail divided by spacing is easy. V is easy. V and I are constant. The difficulty is always, what is the Q? Am I right? Right? What is the Q to consider? Okay. So let's look at this part now. Okay, I'm going to copy this diagram. Okay, we need this diagram. Okay, we need this diagram over here. So I'm going to sketch this diagram out. Okay, we're going to sketch this diagram out. Because, okay, before we sketch anything, where is failure going to occur? Okay, so failure is going to occur either at the intersection between the top flange, okay, and to the web, or the intersection between the bottom flange and the web. Okay, so we have to know what first moment of area to take. Okay, so if we look at this section over here, okay, so consider whether should I draw or no. No, I think we are okay. Okay, so we know that, so let's consider, failure at the top flange and vertical web. Okay. So what is the first moment of area to consider? So the first moment of area to consider, okay, for the top flange is this entire area that I'm going to color in yellow, in yellow. So is this entire area. Why is that? Because you have a Q coming down. You have the force coming down here, V, right? So you have the shear flow. If we were to sketch the shear flow, okay, so we know that this is the Q, right? And then it will come this way, okay? And then it will come down here. Okay, so this is 1 point, 2 point, 3 point. The top part is very unique, okay? So for this case, right, you just need to remember the member distribute the shear flow. Number one thing to remember is the member, right, distribute the shear flow. Okay, it distributes the shear flow. So you just need to remember that. So the entire member at the top will distribute the shear flow first. Then it will transmit the what? Then the fastener will transmit the load. So the member will distribute the shear flow first and followed by the fastener will transmit the shear flow to the web. Okay, just remember this what the member is going to do. So with that context, then it is easy to consider what area to consider. Okay, why I say that? Because you might think, Eugene, why don't we just stop in this area down here? Why not just consider this area? Yes or no? Based on thin wall analysis. So this is not exactly the same like thin wall analysis. It's a hybrid, right? So you have to have this concept that the member will distribute the what? The shear flow. Okay, so that's why you have to take the entire thing. So what I draw the box just now is wrong. Okay, right. So before we can go on, so we know that Q is equal to the resistance is what? The resistance given to us is 50 pounds, right? Divided by the spacing, and then we have to include a 2 down here. This is because left and right. Let me have some space. Nails. That's why we do a 2 down there. So this is equal to 50 pound per inch. Okay. So we know that. So we know that the formula that we're going to apply is Q is equal to V Q over I. Okay. So V is what we are trying to find. Q we don't know. I we don't know. So we are going to quickly find the I. So we're going to find the centroid very quickly. And we're going to find the I. Okay, so we have our we're going to determine our centroid first. So we have our section. I'm going to do this quickly. Okay, so this is our top flange. Then we have our our webs, left web